Hello everyone. So in this particular video, we are going to see what will happen to the alternator if the rotor is supplied from AC source. Basically, if you see the alternator working principles and all, the rotor of alternator is supplied from DC source, and because of the DC source, you will be having fixed north pole or south pole in the rotor. And if you rotate your rotor, then the conductor that are placed in the armature, that conductor will face rate of change of flux, and because of that there will be induced EMF in the rotor, in the stator armature conductors and the coils that are located in the stator. Now, to understand what will happen if we supply the rotor from AC, let me explain what will happen if the rotor is supplied from DC. That is the actual working principle. If we understand this one better, then you will get much more clarity if there is a rotor supply from AC source. Okay. Now I have given a rotor supply from DC, and it has fixed north and south pole. Now you have to rotate this particular rotor with some omega speed, and then there will be voltage induction and all. So to to calculate what will be the induced voltage in the AA dash coil, let's say I have this AA dash coil and it has n number of turns. Okay. So to calculate the voltage induced in AA dash coil, you have to calculate the flux linkage first, that is phi. Because once you know the flux linkage, you can calculate E is equals to d phi by d psi by dt. Okay, this is the induced EMF in the AA dash coil. Okay, and the psi is nothing but n into phi. N is the number of turns and phi is the flux. So we have to calculate the psi or even phi, whatever you have, like, you can calculate. Now, tell me one thing. Let's say your rotor is rotating in anticlockwise direction with mechanical speed of omega m. In this case, I am considering the two pole machines. So, omega mechanical and omega electrical both are same. Okay. Now, let's say at t equal to 0, your rotor position is like whatever I have shown in the figure. This was the rotor position, and after some time t, the rotor will definitely rotate from its original position. If the rotor is rotating in anticlockwise direction with a speed of omega m, then after t time period the rotor will cover omega mt angle, right? And here we have the omega m and omega e both are same, so we can write omega et angle. So this much angle will cover. For example, let's say this was my rotor. This was my rotor. At t equal to 0, it was at alpha equal to 0, at t equal to 0, and after some time it will come here, right? It will be, the angle will be alpha omega et, and basically your rotor position will be at that time maybe something like this. Your rotor position here, like your rotor will rotate, like this is the black one was the position of the rotor at t equal to 0, and at any given instant of t your rotor will rotate this much amount of angle. Okay, so there will be a change of flux with respect to a dash coil. Now it is, and this I hope it is clear like how your rotor flux will rotate. Now if I try to draw the flux linkages, see at alpha equal to 0 you have maximum number of flux lines that is passing through a dash coils, because once your rotor is located in this way, you have maximum number of flux that are passing through a dash coil, a dash coil. Okay, now at some amount of time your rotor will move like this, and flux line is like this, and your coil is located here. So like compared with this initial position, in the second position you have less number of flux that are passing through the coil a dash, and at t equal to 0 you have maximum number of flux lines, and at t equal to at given time maybe some t time after some t time, your flux lines are decreasing. So you can also see in this way, like if you want to draw the flux linkage as waveform or flux waveforms with respect to omega t, let's say with respect to omega et, we want to calculate the flux linkage or phi. Let's say I'm going to calculate the phi of t. Phi of t at t equal to 0, I have maximum, and as I go towards if I locate the rotor at 90 degree, let's say 90 degree means your rotor is somewhat here, and you have coil A dash. In that case, no flux lines are passing from the A dash coil because they are perpendicular. Like here, the coil direction is in this way, and the flux is flowing in this way. So there is 90 degree in between those two. So there will be no flux linkage at 90 degrees. So at 90 degree, the flux linkage will be 0. So at t equal to 0, it is maximum. At t equal to 90 degree, it is minimum. So that is basically, we can say it is the cosine waveforms. This 90 degree, this 180 degree, and here it will be 360 degree, right? Here it will be 270 degree. So this will be the flux linkages waveforms. Okay, so let me erase this part. And what will be the equation of the flux linkage of t? Phi of t. Phi of t is nothing but it will be having some maximum value, that is flux per pole cos of omega et. Okay, this is the flux linkage waveforms equations. And here the peak value is flux per pole. Like the flux per pole is the maximum value, and as you rotate, that flux per pole value will decrease, and it will be cosine in nature. Now you have the flux linkage, that is psi of t is nothing but n phi of t, n flux per pole cos omega et. Now you can calculate the induced voltage in the coil A dash, d phi of t by dt minus n flux per pole omega e sin omega et. Okay, so this science and all you can ignore if you consider the Lenz law and all. So that those things will vanish basically. So you need not even worry about that. So this is the magnitude, and the a sinusoidal induced voltage you will get once you have a DC excitation in the rotor. But what will happen if the rotor is supplied from AC source? That is something that we have to see. Let me erase this portion now. Now let's say you are supplying this field voltage from a AC source, VF, it is AC source. Okay, and if it is AC source, let's say take a cosine waveforms. Let's say your current, that your field current IFT with respect to t, it is cosine in nature. So till this period, if my rotor is producing north pole and south pole in this direction, during this negative half, the polarity of the rotor will simply reverse. Like then this will be your south pole and this will be your north pole. So your rotor poles are also rotating, and at the same time, like rotor poles are the direction or the polarity are reversing in each half cycle. At the same time, your rotor is also rotating. So you have two phenomena is occurring at the same times. Okay. Now it is clear, like right, because of the alternating field current, your rotor poles will reverse, and at the same time your rotor is also rotating. So let me write down what will happen. So basically flux phi of t is nothing but mmf by reluctance, and mmf is nothing but number of turns and current by reluctance. So it is the current, and here you can say it is a field current. So your phi of t is proportional to the field current here. Okay, this is clear, right? So I can write maybe we saw in the previous like derivations and all, like because of the DC we were getting flux waveforms. Phi of t is nothing but flux per pole cos omega e t, right? This was this I was getting, and this omega e t, what I was mentioned at that time, it is nothing but the alpha. Alpha is nothing but omega et, because after t time your rotor will rotate and it will achieve some angle. So that angle is nothing but alpha is equal to omega t. So you can also represent here like this way: flux per pole cos alpha t. Okay, I'll explain why this alpha is important and all. And here you cannot represent the flux per pole constant because it is varying. So if my current is cosinusoidal in nature, so my flux per pole will also be cosinusoidal in nature, you can say. So your flux per pole, you can simply write flux per pole cos omega supply t and cos alpha t. Is this line clear to all of you? Like how I could able to write this point instead of this high pp. Okay, let me explain you one more time. Uh, See, when you have DC supply, when you have a DC supply, you could able to write phi of t is simply flux per pole cos omega et, and omega et nothing but cos alpha t, phi of t flux per pole cos alpha. Okay, now the flux per pole is not constant in this alternating supply. It is continuously varying, like north pole, south pole, north pole, south pole. That variation you have to consider. So to consider that variation, you can only you have to consider the effect. Like so, since I have the alternating currents that are, let's say, it is cosinusoidal in nature. So basically, it is a cosinusoidal curve. So it is maybe some cos omega st, and it has also some peak value. So because of that peak value, I am getting phi of t is equals to flux per pole cos omega st and cos alpha. Okay, so this is the flux equations that you are getting. Okay, now you have to calculate the induced voltage, but before we go to the induced voltage, this equation is very important. Basically, like it is a very special equations. In the later point of time, I will discuss two types of waves are there. Like there is something called traveling wave, and there is something called standing wave. And this particular equations, the equation number one is basically it is a standing wave. Okay, and these things I will discuss in the operating principle of the single phase induction machine. So as of now, we can just remember like it is a pulsating waveform or it is a standing waveform. So what will happen if I maybe if I resolve the equations or if I rearrange these equations, let's say phi of t flux per pole by 2 cos omega st cos alpha t. So you can write phi of t. Omega is basically supply frequency of the field current, cos omega st plus alpha cos omega st minus alpha t. So this is the things. Sorry, it is not alpha. Extremely sorry, it is just alpha. So here also t will not come. So you have this particular equations. Okay. Now let me erase this portion also now. And alpha is nothing but omega et, right? So I'll just put omega et here. Phi of t flux per pole by 2 cos omega s minus omega et plus cos plus is equal to plus omega s minus omega e t. Okay. Now, let's say your rotor is rotating at synchronous speed. If your rotor is rotating at synchronous speed, then what will happen? Please focus on this. If your rotor is rotating in synchronous speed, let's say the mechanical synchronous speed is omega sm, and as I mentioned, like the it is two pole machine, so the omega sm is exactly equal to the omega electrical, like omega electrical angle, electrical speed. It is mechanical radian per second, mechanical radian per second, and this omega is the electrical radian per second quantity, electrical radian per second. For two pole machine, these two are same, these two are same. So, and also your field current supply frequency is omega, that is nothing but synchronous speed. So basically, if your rotor is rotating synchronous speed, then omega s and omega e both are same. If both are same, then what will happen? This particular quantity will simply vanish, it will be 0, and flux per pole quantity will be having flux per pole by 2 cos omega s plus omega e t, and it is the twice of the omega supply, so I can write twice of the omega supply. So you can see now you have this phi t. Now you can calculate the induced EMF. Let me raise this here too. The induced EMF E of t is equals to n d by dt of flux per pole by 2 cos 2 omega s t. So it will be half n flux per pole 2 omega s minus sin 2 omega s t minus n flux per pole omega s sin 2 omega s t here. So magnitude seems the same what I was previously, like with the help of DC supply and AC supply. In the both the cases, the induced voltage are same, but the frequency becomes twice of the supply of the field excitation. Whatever supply frequency we have in the field excitation, we are getting twice of that in the induced EMF frequency. If the frequency of the induced EMF increase, then what will happen? There are many things that can happen, like the core loss and all those things will increase and decrease, all those phenomena and all those analysis can be done depending on the frequency increase. Okay, but it is not a good thing because it has several detrimental effects and all in the entire power system network. If you are interested to know like what will happen if there is an increase in the frequency, we can discuss these things in later, but as of now I feel like it is clear to all of you, like if we give the AC excitation to rotor, then what will happen to the induced EMF. Okay, if you have any doubt you can ask me in the chat box. Thank you.